So, welcome, good morning. Good morning. Okay, cool. So, today I'll be talking about, I'll give an overview of every technology, I would say, which is predominantly available in the industry, and also talk about some of the memory subsystem architecture at server level, right? So that is more important than going into technology. Once the technology matures, you have to be able to use that in server memory subsystem or high performance computing. So today I will be going through, starting from fundamentals, DRAM, DDR3, DDR4, and what is coming next, and DIMMs, memory controller, and then look at server memory subsystem architecture, like direct attached or buffer based or whatever different memory subsystem architecture, and then look at what is currently available in the emerging space in the memory subsystem, and then look at nest architecture. So if you have enough memory size, you should be able to use that in the nest architecture also. So when you develop this, you should be able to upgrade yourself on the nest also. And then finally I'll touch upon IBM Power 9 architecture, and where you can influence and utilize the power ecosystem and contribute to open power technology. If you have any question, you can stop me. Okay, we can make it more interactive rather than preaching, right? Okay. Okay, so this is the overall memory hierarchy as it stands today. It I put Power 9 architecture at the right side. So it has got 12 to 24 core, okay, and it has got L1, L2, L3, shared L3. It goes up to 2 MB to 8 MB. L2 is 512 KB, and L1 is 32 KB instruction and data. And then we have got multiple memory controllers inbuilt, which can be directly attached to the DIMM, dual inline memory module, I would say here, dual inline memory module. And then you have NVM, it's called NVDIMM. And then going forward, you will have SSDs and hard drive. So basically you have starting from registers all the way up to HDD. On the capacity side, it is too small starting from the top, and then it goes very huge in case of HDD. But on the other side, latency wise, HDD is pretty much slow in terms of milliseconds, and fast will be as fast as like nanoseconds, 1 to 2 nanoseconds. Okay, this is the overall memory hierarchy in which you talk about capacity as well as latency. Today the talk will be focusing only on this. My talk will be focusing only on this, starting from memory controller, DRAM, DIMM, and then some of the emerging memory technology. I stop at NVM. I don't go to SSD and HDD. Okay. Okay. So fundamentals. How many of you are aware of the memory subsystem architecture? I know all of those guys are aware of it. Okay. Okay. So DRAM is pretty much considered as it has got. Oops. I have to go slow. Okay. So it has got a transistor and a deep trench capacitor. If there is no charge, the logic is 0. Okay. If there is a charge on the capacitor, you can read that, and then you get logic 1 through the sense amplifier. Okay. So this is like a leaky bucket, right? As soon as you charge, you cannot keep the charge forever, right? It will drain after some time, right? So you have to keep refreshing in order for you to keep the logic inside the capacitor. And this is one DRAM cell. If you want to put that in an array, you will have a row and column. You call it as word line and bit line, and then you have a row which is consisting of multiple cells together, and then this comes to a sense amplifier, and then to a row, it's called row buffer, and then it will come outside of IO gating logic and then go out of the DRAM, right. So, I have started working from SDRAM time frame. 1999 I started my career. That time I was working on 133 megahertz SDRAM. Now we are working in 3200 DDR4, right. So, it evolved from SDRAM all the way up to DDR3, like 2 years back. Now we are at a point where we are currently working on DDR4. So, DDR4, right. So, DDR3 versus DDR4, I think most of you are aware, right. DDR4 can go from 1600 all the way up to 3200. Okay. Right now the speed is, I would say, 2666. Predominantly all the companies are using 2400 speed at the single drop, and dual, I would say single drop is 2400 or 2666. Dual drop can go up to 2133, right. And the device density ranges from 2 gigabit all the way up to 16 gigabit. Currently in the market what you see is 8 gigabit and then followed by 16 gigabit probably next year. And it has got bank groups and banks. In this case you do not have bank groups. DDR3 does not have bank group, but in case of DDR4 you have bank group, and each bank group has got 4 banks. Okay. So, overall 16 banks you will get in DDR4, and then the row size or the page size will vary from 0.5 KB all the way up to 2 KB, right. And the supply voltage is 1.2 compared to DDR3 1.5. DDR3L, there is a low voltage DDR3 is also available, that is 1.35. So, directly as you can see, you can save lot of power by supply voltage and also some of the ODT termination technology, which is called POD, pseudo open drain, and then this is center tapped, right. This will have 2 resistor and this will have only 1 pull up resistor. So, you will save half the power, right. So, overall you will save about 20 to 40% of power, right, compared to DDR3 and DDR4, and the speed is much higher compared to DDR3. I will not go into all details, but some of the key activities, I would say write VREF DQ. So, inside the DRAM you will be able to set up the DQ reference voltage very clearly, right. In case of DDR3 it is divided into 2, like if you have a 1.35 it will be 0.675, right. That is VREF DQ, that is set. Here you can vary that depending on the DRAM. Okay. Any questions so far? Yeah. So, I think I should say that in DDR3 it is 8 banks. It is like a page where you will have rows and columns. Okay. I will probably tell you in the next slide if you are okay with that. Okay. So, this is the DRAM internal. As you can see, there are multiple blocks in it. So, whenever the address lines and data lines comes from the memory controller, if you want to address any DRAM for that matter, you will be sending the address lines in this and it will come to a row decoder, right. So, you have to be able to select the row and activate that bank. So, that is the first operation in DRAM. Any memory subsystem, if you want to access anything, whether you want to do a read or write, you should be able to activate that bank, right. So, once you activate, so you will get the address lines, you will be able to decode the row address and then activate that bank, followed by you will be giving the column address, you will be able to get that entire content into this IO gating logic through sense amplifier. So, sense amplifier will get about 8K bits, 8.192, right. 8192 bits will be in this IO gating, and then the column decoder will select only the column which it needed and then get it to the read latch or write latch. So, if it is reading, you should be able to give read row address, column address, and then take the data, read, you will select only the 64 bits and then give it to these output pins which are 8-bit. So, there are DRAM devices available in by 4, by 8 and by 16 device width. So, in this picture, as you can see, this is DQ0 to DQ7, there is only 8-bit which is coming out, but you have about 64 bits, you have already taken it like a prefetch, right. So, you will be sending this in terms of 8 bits at a time, that is called burst length 8, right, BL8 or BC4, right. So, you will be able to send the data continuously. If you have a write, you will be able to get 64 bit at a time, okay. And if you want to write, you will be able to send 64 bit 8 bit at a time, and you should give the column address and then write it back to these cells, okay. Any question? Yeah.
What is the reason that we need VC4?
So, say for example, if I do not try to use the entire bandwidth, I do not want to use the entire bandwidth in the data bus utilization, right. If you want to use half, but still you need to comply to DDR3 or DDR4 standard. So, you will be able to get 32 bit at a time, and if the cache line size is only 32 bit, nowadays I think it is available in 64 and 128. However, you want to take it 32 bit, 64 bit or 128. Currently what we do is we take about 2 64 bits and then fill the cache line, okay. So, that is how you can imagine. Yeah, writing. So, what you should do is, I think when you give the row address, you have to activate the bank, okay. Once you activate the bank, you give the column address also, and then you have to send the data and then write it back to this location, okay. You need to wait for certain amount of time, it is called write latency. It can be, I think I have a slide which talks about all timing parameters. So, there are some of the key parameters in DRAM, right. If you want to be expert in this, you should be knowing all these timing parameters. So, initially you start with activate, that is the bank activate which I told you. Activate to internal read or write, this is called TRCD, row column delay or RAS to cache delay. And then once you do that, then there are other timing parameter, it is called pre-charge. Once you wrote into the row, if you want to write into other row or if you want to read into other row, you have to close the row and then come back to the next one. So, it takes about TRP time to pre-charge, you have to write it back and then come out, right. And then activate to activate, between two activates you need to give certain amount of time because DRAM needs that time, TRC. And then T4 is 4 activate window. So, there is a current limit in the DRAM vendor, right. So, you cannot keep giving activate continuously because the DRAM power, the current requirement cannot be handled. So, there is a limitation by the vendor. You can send TFA, which means that 4 activate at a time you can give, but then you have to wait for certain amount of time to give the another activate, right. And you can see any of the DRAM vendor, if you want to select some of the DRAM, you need to be choosing these, okay, based on your latency. You can choose, for example, in 2666 it requires about 19 clock cycles, TRCD, TRP and CL, right. And then the next one is activate to pre-charge. So, you have already activated, but if you want to pre-charge, you have to wait for TRAS time. And there is another 2 timing parameter which is activate to activate for a different bank group, right. You have activated one row, but row to row on a different bank group will have different timing. So, that is called TRRD, row to row delay, short and long, right. And then the same with column also, column to column delay, short and long. And then you have refresh, and then between refresh you cannot keep giving refresh, you have to wait for TRFI, which is like 7.8 microsecond and 3.9 microsecond if the temperature is very high, okay. 85C 3.9, if it is regular temperature it is 7.8, okay. So, this is the simplest DRAM functional state diagram. Oh, sorry, question. Yeah. There is a activate time which DRAM takes about TAA time to respond. That I have not told here, right? Okay. So this is the simplest, okay. Okay. So simplest state diagram. All the banks will be in idle mode to start with, and then once you want to do activate, you have to get into activate mode, and once you give the activate command, the bank gets activated, and then you can do read or write with the precharge or without precharge. That's called auto precharge, or you can send read along with the precharge, right? Okay. So this slide talks about Moore's law. Generally, we talk about Moore's law in case of logic chip, right? We say that Moore's law is not really giving up the technology nodes what we wanted. So in this, if you see, this is from 1994 all the way up to 2018. That's where we are currently today. So we have been lagging behind on the density, but the requirement on the density is going very high. Currently we are at 8 gigabit. I would say we are also in 16 gigabit manufacturing, but the cost of the DRAM is very high. DDR4 is the only technology currently available. DDR5 is not standardized yet, right? So all the vendors have increased their price, doubled. I mean, basically they have doubled the price. There is no other way for us to move to any other technology, right? So that is the point which I wanted to make here, that we are not yet there, but we have some good amount of density to make up. Okay. Okay. So far we talked about DRAMs, some fundamentals. Now we will get into DIMM. We talked about this one chip, right? Now we put all these chips together and then form a DIMM, right? Dual inline memory module. Okay. Okay. So DRAM, as I talked about, it will have these many pins: command bus, address bus, data. Totally you will have about 38 pin, right? But in case of DIMM, you will have command bus, address bus, data. It's all same, right? But as you can see, the address bus is 19 pins only. Okay. The data is becoming 90 compared to 10. Okay. Why? Because the address is shared between all the DRAMs, right? But the data is not so. Data is coming from each of the DRAM, which is like 4-bit or 8-bit, right? So if you want to form a 72-bit, you need to have 9 into 8, right? So it should be a 8-bit DRAM, which will give you 72-bit, right? So this is a old data, 16. I think right now we are at 2666. So and we can also go up to 128 gigabyte. Okay. So can anyone say why there is 9 DRAM instead of 8? We need only 64 bits, right? Why do we need? Okay, good. Yeah. Okay. So we cannot live with one DIMM only, right? We cannot have density which is like 128 gigabyte. The entire server cannot live with 128 gigabyte, right? We should be able to expand that memory subsystem with multiple DIMMs, right? So how do we do that? Is we give the same address line, right, to the another DIMM also. Like it can be another DIMM or it can be in the same DIMM with multiple DRAM chips. The address will be shared between all the 18 DIMMs, DRAMs, 18 DRAMs, and then between these two you can select these rank. We call 9 DRAMs as rank. Wherever there is 72-bit coming out, that is called rank. So this is one rank, this is one rank. You can select that with the chip select, right? Basically address, if you go A14 to A15, you can select with that bit, you will be able to select between two ranks, right? But still this is not enough, right? So we go for bigger and bigger DIMMs. Say for example, there are short DIMMs available, long DIMMs available, this is 240 pin, right? This is another question. Can anyone answer? Nobody knows the answer? I know those guys knows, but I want to. Okay. Okay. So basically DDR3 has got 240 pin, right? And DDR4 has got 288 pins. Okay. Generally we use 288 pin server DIMMs. There are multiple DIMMs available. And now we have seen the density, but we need to now be able to go to the frequency, right? We cannot stay with the same frequency. So in 2005 it is about 533 megahertz. Like in 99 I worked at 133. Now we are at a point at which we are working at this frequency 2666, right? But then DDR4 is further going to 3200, which you will see in the standard probably next year, 2018, right? Okay. So can we keep on adding DIMMs in order for us to increase the density? Is that possible? Yeah. So that's a good answer. So you cannot keep sending the address, and you cannot share. In this, if you see, there are 36 DRAMs which need to be shared with this address line, right? The address line will have sourcing current, sinking current, all those things has to be taken into consideration. And then the DRAM will have an input capacitance. If you add all these input capacitance and then try to find out the fan out, that may not be possible, right? So you cannot try to address one pin with so many DRAMs, right? So you should be able to take care of this loading factor, right? Rank 0, 1, 2, 3. We generally call 0, 1, 2, 3, but you can also call rank 1, 2, 3, 4. So the address is shared between all of them, but the DRAM data is not, right? So there are multiple other DIMMs are available to take care of this, right? That is called load reduced DIMM, right? So the memory controller will have will be able to connect to register DIMM with the help of register, right? Where you can take the command address, you can buffer that and then send it out to all the DRAMs, right? By which you will be able to increase the source current of that address pin, and you will be able to increase the number of DRAMs, okay? And also this is only for address, right? If you are trying to do that for load reduced DIMM, which is having a memory buffer, which means that register there will be RCD and also a data buffer, right? In this picture I have shown only memory buffer, but there are two chips available. One is data buffer, the other is RCD, right? So you will be able to buffer address and data together, and you will be able to drive furthermore. So in this case, if you see, if you put in signal integrity circuit, here you will see driver, receiver, and then multiple receiver here, right? So the same way here, for everybody, one driver, one receiver, and then internally you will be able to send it to multiple DRAMs, okay? This is basically to avoid signal integrity issues in the board, right? Okay. So you can also do with the register DIMM, multiple DIMMs can be connected. So this is called single drop and dual drop. So basically you will have a memory channel which will have a 2-drop configuration. Both the drops will share the same address line, but the data will be different, right? 64-bit will come from either of this or this. So we call it as rank 0, 1 from this DIMM, and then 2 and 3 from this DIMM, okay? And in order to increase the performance, we generally do a rank interleaving. Rank interleaving is already taken care of the DRAM. At rank interleaving, you will try to get 64-bit from here and then 64-bit from here, so that you will do odd and even and then try to fill the cache 128-bit. And then the memory channel capacity, we have been in 133 you can connect multiple channels, right? With one memory controller you will be able to connect multiple DRAMs, DIMMs, but going forward because of the speed signal integrity problems, you cannot go beyond 1 or 2 DIMMs, right. So, that is the problem which we need to address. How do we do that? So, that then it comes stacking, right. So, where you will be able to, in this picture as you can see, multiple DRAMs are there, right. So, all those 4 DRAMs, for example 1, 2, 3, 4, right, all those 4 can be stacked like this, in this way. There are multiple other techniques available. This is only wire bond. You can do it with the 3D TSV, which I will be talking about. And currently you can see the device density is going up to 16 gigabit. You can have 8 ranks also with the LRDIMM, right. And then the current density at RDIMM 3D TSV is going up to 128 gigabyte. Okay. Okay. So, this is another which you would like to know, right, by 4 and by 8. So, if you see these two are very similar, right, very similar DIMM, right. So, this is called 2 gigabyte. We call this as, we do not call by ranks, we call with the density, right, 2 gigabyte. 2 gigabyte 1 rank, you have about 18 DRAMs which will constitute 2 gigabyte. This is 2 rank 1 gigabyte, this is 1 rank, this is 2 rank, right, but here it is by 8 chip, this is by 4 chip. So, you will have same number of DRAM count and same density, but the rank will be varied. Okay. I hope this good, right. Okay. So, we have seen DRAM and followed by DIMMs, right. There are other things which are in the DIMMs which I have not talked about is RCD and then SPD. SPD is a serial presence detect, where you will have all the manufacturing data of the DIMM vendor, right. It can be Micron, Samsung, Hynix or anybody. They will have their own ID and the details of all the timing parameter. When you plug in, you will be able to read all the timing parameter from the SPD. And then you also have PLL and DPLL, and it can go up to 72 bits with the ECC. Okay. I just wanted to touch upon memory controller. We saw DRAM, DIMM, and then it comes to memory controller, right. So, you have last level cache, it can be L3 or L3, and then it can be also nest architecture wherein the data is coming. You have once you get the data input packet, you will be able to do address mapping. You snoop the address and try to get all the data and then put them into read or write queue. This is a command queue, right, multiple command queues. Once you get into the command queue, you will be able to send that through a scheduler, right. If you have a write or a read, you will be able to send that through a scheduler, and scheduler will wait for DDR4 timing protocol. It has to comply to that, right. So, I have not really specified read reorder queue and write reorder queue. So, basically why this is required is if you want to improve the performance, for example, right, you have already opened a page and I want to read multiple times, and I have a read queue which has the same page which is already open, the read is slightly below. Then I can use the read reorder and then try to move that up so that you can improve the performance, right. So, you can do that, and then you have page table maintenance engine which will do MCBIS, memdiag and scrub, right. Scrub is required in case of server environment. We do scrub once in 12 hours or 24 hours, right. So, basically we scrub through all the memory location, we try to read and do a read modify write, right, in order to make sure that there are no any soft errors, right. And currently we are at 2666 frequency, we use double data rate. Okay. Okay. So, we talked about all these things, right, memory controller or memory buffer. Now, we will talk about the entire subsystem architecture. Okay. So, there are multiple ways to connect DIMMs to the processor, right. One is direct attach. In this case, I am showing Power 9, IBM Power 9 processor, where you can connect DIMMs directly from the processor memory controller. You can attach 2 DIMMs per port. So, you will we have about 8 ports, 8 into 216 DIMMs we support. if you consider one DIMM size is 128 gigabyte, we will be able to support up to 2 terabyte processor. Generally our processor supports more than a terabyte, right. This is used in high performance computing and also cloud and big data and other machine learning and artificial intelligence kind of application. And then the other one is Skylake. This also has direct attach. You can connect to 2 DIMMs per channel, and I have also seen there are some 6 channels per processor, right, Skylake. And then this is from AMD, EYPC is a processor name, and you can connect direct attach. Okay. So this is one of the architecture where you can connect processor and the memory subsystem directly. The pros and cons is like the processor you need to be changing. For example, if I change from DDR3 to DDR4, I need to be able to support 288 pin, and also should be able to change the pins, which means that processor has to respin, right. Processor respin is not a joke. It is a multi-million dollar expenditure. So you cannot do that. So there are some limitation with the pin number and then the interface where you can connect, but the advantage is that it's very simple design, right. You can take the DIMM, connect the processor, you're done, right. This is the old other technology wherein you have another chip which will take care of north bridge. So basically this is the Intel architecture where you have CPU, north bridge, and then you can connect memory bus, right. So there are pros and cons. Here the failure rate is multiple places. It's not that DIMM or CPU, you have another point of failure, and you also have power consumption of this chip. So that is also more, right. So this is another way of connecting the same thing. Instead of north bridge, this is IBM's memory buffer, where you have memory controller and then memory buffer. So some of the memory controller functionalities are offloaded to buffer, so that you can do multiple other things on top of memory controller what it is doing. And the advantage of this is, if you put a buffer, you can connect DDR3, DDR4 or 3D TSV, any technology for that matter. The memory controller buffer should be able to support that, and you can you don't need to respin every time. So that's the advantage of this. And you can also scale up by connecting the buffers together, right. So we do that in Z server, right. So the same buffer can be used in different format. One, the buffer can be put onto the DIMM. The second is you can put that in the motherboard, right. This can be on the motherboard or it can be on the DIMM. Okay. This is again Power 9 with the memory buffer and DIMMs. Okay. Okay. So we saw DRAM, DIMM, and then memory controller, server memory subsystem architecture. Yeah.
Quick question on the previous slide. Since your Power 9 supports both direct attach as well as this buffered architecture.
Correct.
So are these two different variants of the server?
Correct. So now we have a Power 9 processor with the different pinouts. So we call different module called Monza, Lagrange, and Sforza. Sforza is for the low end one, Monza is for high performance, and Lagrange is for enterprise. Okay. So overall, server looks like this. After going through all the thing, you have processor, memory buffer, you have DIMMs. This all put together forms a server memory subsystem architecture, right? Any questions so far? On a daily basis, we work on this. Okay, we design till volume manufacturing. We have to handle everything. So there are some challenges in DRAM. First thing is scaling, power, bandwidth. Are we hitting the memory wall? That's the question, right? It's been there for a long time, right? But still, we are able to make progress on DDR interface. And then there is a speed mismatch between processor and memory, because currently our processor can run up to 3.6, 4.2, and Z processor can run up to 5.5 gigahertz, but the memory is like now we are at 2.4 or 2.6, right? So there is a mismatch. and then increasing per core per thread memory requirement is always increasing, it's not stopping, right. And then there is a board level signal integrity problems. You cannot route 6 gigabyte or 4 gigabyte signal very easily, right. So you should be able to take that challenges. And then additional energies, right. If you keep on adding components, keep on increasing the frequency, the memory power will be a problem. So what do we need? We need high bandwidth, very small form factor, and then low power. Do we have any memory technology which gives this? The answer is no, right. So we will, I think exactly 30 minutes, I come to the right point, okay. I'm on time. So we will go through current and emerging memory technologies. I'll give lot of technology overview. I may not go in depth, but because each of the topic will take about 1 hour, right. We will not be able to cover, but there are experts sitting there who will deep dive into some of these. I'll try to give overview on available technologies, right. So this is 2.5 or 3D TSV stacked DRAM or logic chip. For example, you have package substrate which will be sitting and interfacing with the memory controller, okay, and then you will have a logic chip which will talk to all the DRAM layers. So this is connected through TSV, this is called through silicon via, right. So this is typically like a via which will connect between the chips, between the dies, right. So the advantages, multiple advantages, you can consider this like like an apartment, right, instead of a row house or a villa, right. That is individual DRAMs, but you can stack everything together, you can form a high density DRAM stack, right. And at the same time you can also form interposer, which is a small PCB which will be sitting above the PCB, and that can communicate with the logic memory, and it can also be in this format. So all can be done with the TSV, right. So the challenges is how do we do power delivery? For example, logic will need 0.9, memory needs 1.2, and RF circuits are there. So multiple problems are there. So as a research point, I would strongly suggest for you to consider these challenges and then work on your PhD or MTech thesis or whatever, right. So thermal distribution, for example, you have 4 stack die here, right. You have a logic layer which can dissipate energy through a ground layer in the PCB, and then at the top you have a heat sink, right. It can take out the heat from the chip, but what will happen to the middle ones, right. There are problems, thermal challenges, you cannot distribute thermal problems across the stack. So you can work, yeah. So yeah, that is called through silicon via. So as you can see, there is a silicon via which will connect all the dies together, and then you have to select at the bottom there is a multiplexer where you want to get the data, you can select that, okay. And then there are yield problems, implementation cost is high, but it is coming down drastically, okay. Okay. The other technology which is interesting, which gives very high density, is HBM, high bandwidth memory. Earlier the other technology is called wide IO. This is a improved version of wide IO, and similar to this RAM bus has got GDDR5. So typically these kind of things is used only for the graphics, right. So NVIDIA predominantly uses HBM. As you can see, this is a Volta 100 graphics card, I mean GPU card, which we predominantly use in Power 9, right, CPU, GPU with the Volta 100. So it can go up to 1024 bit wide access, immediately you will get the data in very wide bandwidth, and you can go up to 8 gigabyte or 16 gigabyte per package, and very high bandwidth. If you want to run an entire application from this, you will be able to use these kind of high density memory technologies. Next comes a hybrid, yeah.
So, again, last slide. So is this HBM sort of any different from the 3D stack or HMC from Microsoft?
So for example, in this case, if you see, there is a it is all similar fashion, I would say. It is all similar where you stack the DRAM core and then try to get the more density outside, right? But in case of this, the IO numbers is very huge, IO 1024 wide IO, right? But in case of HMC, if you see, this is, I would say I should go to this, right? This is using high speed serial links, right? So you can have a protocol on your own and you should be able to send your packet to the logic die and then try to get it, right? This is another way of doing the same thing, but this is from Micron, right? So HMC is also like you said, similar technology which will give very high density, where you can form a cluster kind of a memory, I would say memory mesh between the process, and you can also connect, if you want to use this as a cache, for example, HMC can be used as a cache if you have a same interface which can go to multiple memory technologies, right? So you can immediately get high density data from the HMC, right? Okay. So far, even I think 2 years back when I was presenting this, everybody was saying DDR4 is the end, we are done, right? The answer is no, right? Because we are currently working on DDR5 SDRAM, standardizing, standardizing body is JEDEC, and we are currently working with multiple other companies, IBM, Intel, Qualcomm, Google, name all the companies. So DDR5 is coming, right? DDR5 is coming with a very, high improved performance and great power efficiency. Currently, the DDR4 goes up to 3.2 gig, right? In DDR5, I may not be able to share all the data, but DDR5 will go up to 6.4 gigabytes per second, right? So DDR5 will be coming in, I would say 2008 end time frame. The standard will be ratified by that time, and 2019 the chips will come out. When the DDR4 and DDR5 the cost comparison comes, probably in 2020 or 2021, it will be much cheaper, equal to DDR4. Okay, and I would say some of the architectural changes, it will have probably 32 banks instead of 8 or 16 banks. It will have bank group which will have only 2 banks, not 4 banks, because you cannot at that speed you cannot go between the bank groups or banks inside the bank group. So you will have those kind of architectural changes, many of them which I cannot share in the forum. So the other DDR interface which is very promising is NVDIMM, non-volatile DIMM, right? So in this case I am talking about non-volatile DIMM N. N is one of the standards which I will talk in the next slide with the other variants. So this is also coming in DDR4 and DDR5. They have Smart Modular and Micron, they have released DDR3 based NVDIMMs. It was not really a popular one. Right now I think DDR4 based NVDIMM is popular because of multiple reasons. Here in this case, how this operates is you have multiple DRAMs. It's very similar to DDR4 DIMM. Only thing is that you will have a controller. If the power goes off, right, it will take all the DRAM content and save it to NAND flash. So in order for NAND flash to power up or the DRAM to power up, the NAND flash is persistent memory. You don't need any power. You need a power, but you don't really need to sustain the data state. You don't need a power, right? So for DRAM, if you take out the power, the state will be gone. So you have to give the supercap based power supply for the amount in which the DRAM data is transferred to NAND in terms of milliseconds, for example. So you can have supercap in different densities based on the densities available in NVDIMM. Currently 16 gigabyte and 32 gigabyte is available in the market. Okay. The important one is save and event. We have also written multiple patents on this. How do we concurrently do backup and restore and those kind of things. And this is another area where you can explore and do research as well for different applications. So, we talked about NVDIMM N, right? This is very equivalent to DRAM, tens of nanoseconds, but the next one is NVDIMM F, flash, right? If you want to use, for example, the SSD kind of a persistent memory in processor interface, right, then you go for NVDIMM F. This is not standardized yet. Smart Modular and other, I think, other companies are trying to do this, but we have not standardized this. This is in, this is also equivalent to tens of microseconds, right, better than SSD. So, you can use this as, cache for SSD, right. So, you can improve the performance of the application by running some of the small application in NVDIMM F, where you can access the data in very high speed, which is equivalent to DDR, right. The last one is NVDIMM P, right. This currently is also in JEDEC, right. We are defining the deterministic and non-deterministic protocol as part of this NVDIMM P. This, what it will have is basically one side DRAM, the other side is non-volatile memory, where you can do multiple action within that, right. You can store the small application which is persistent to non-volatile and high performance one on the DRAM. So, you can do multiple things, and the protocols for security, persistency and all other things are being defined, right. You can do memory mapped or flash mapped. That is the advantage of this, okay. And this will also be coming in DDR4 and DDR5 format. Yeah. Is DDR4. Yes, DDR4 or DDR5. Okay. So far we have talked about all the DDR interface, DRAM interface, right. What is coming next, right? What is coming next? So far we have talked about capacitor based storage, right. Now everybody is going behind resistor based. This is like non-volatile, right. So charge based or resistive based. So all the non-volatile memory going forward will have these kind of cell structure, I would say, right. This is basically from using voltage sensing, this is current sensing, right. I will give an overview of what is coming, right. PCM, it did not take off the way we wanted. It is a non-volatile memory, medium performance, it's all our storage class memory, SCM, right. So there is a structure, material will change based on the when you apply the current. So this is in amorphous phase, logic 0, and then when you want to put it in logic 1, you apply a current and then it gets set this way. So the resistance will vary based on this or this, right. So the logic is defined by the change in material shape or atoms, right. So it takes this in microsecond range, it cannot be replacing DRAM, right. It cannot be replacing DRAM and it cannot be used as a main memory, right, but it can be used just before SSD, right. And then the next one is STT MRAM. This is where I am working with some of the Watson research, and Kalyan and myself also working on some of the researching activities of STT MRAM, where to improve the reliability, right. So Everspin has come up with a chip which is 64 megabit and 256 megabit, right, and this is in planar STT-MRAM. In the next slide, I will talk about a slightly more detailed version of STT-MRAM. And then there is another technology called ReRAM, resistive RAM. This is more beyond like 5 years down the lane. This can probably replace flash and so on, right. This is again atomic structure where you try to align that atoms in a particular way so that the resistance is small or high. Based on that, logic high or logic low can be determined. So out of those three, I would pick STT-MRAM as the leading candidate. So we have some reliability issues and other challenges. I would say STT MRAM or PCM has got high write power and long latency. That is a problem, right? How do we address that is the big research. And reliability issues, write disturb and read disturb. Why? Because this called perpendicular MTJ. This MTJ will be equivalent to the capacitor. The MTJ will be used in place of capacitor in this place. When you try to apply high magnetic field, the electron will spin the opposite direction. How much it spins, what is the resistance, that is the problem, right? How much you have to apply, do you need to apply for a long duration or do you apply with a short duration with a high current? All those things has to be determined. When you apply a high current, what will happen to the neighboring cell? That is a read disturb, right? It is when you read, what will happen to the neighboring cell? What will happen to the read sensing error and so on? So those are the problems, and there is another problem called MTJ thermal stability issues, where you have temperature variations across the DIMM. If you use this in a DIMM, you will have a 85C, 125C, which should not affect the operation of MTJ, right? So you should be able to take that into consideration and then look at resolving all these problems before we get this into server environment. And then currently I would say 1 gigabit STT MRAM is available in DDR4 interface operating at 2133, and this is done by Everspin and also Avalanche Technologies. And 4 gigabit from Toshiba. Toshiba is running through a lot of problems as a company. So they have also done a proof of concept with the 4 gigabit STT MRAM. And many other companies are using this as a embedded memory, because the density is very less. It can be used very heavily on the SRAM side, and consumer electronics can use this as a embedded MRAM, right? Okay, the last one I may not go into details. This is from Intel Micron chart, 3D cross point. So this is very similar to PCM, but in the stacked way, right? You have high density with the help of 3D cross point. This comes between SSD and DRAM, slightly faster than SSD, but I would not say that 3DXP will replace DRAM, will not replace, right? So Intel has come up with something called Optane SSDs and Optane DIMMs, which will be predominantly using 3D cross point. Okay, so with all the hype in memory technology, we should be able to look at something in the nest also, right? We should be able to get the aggregate performance which is coming from memory. We should be able to take it to the processor, right? So what is next in the industry for IO? We predominantly work on OpenCAPI, coherent attached power bus interface. These are the companies vouching for this. Predominantly I would say Google is working on OpenCAPI, standardizing this thing, and there is opencapi.org where you can download all the material, which is very freely available, and you can develop your model and do research on it, right? So IBM is also part of this standardizing committee. Okay, what do we need actually, right? If you want to really design an accelerator or high performance compute node, you should be using some of these high speed interface in order for you to take out the bandwidth which is coming from memory, and also should be able to translate that into a performance, right? So you need a computation and data access, both should be coherently go, it should go well. And the advantage of OpenCAPI is the memory behind OpenCAPI interface is coherent to the processor. That is a key advantage, right? If you change any state in a memory, it will reflect in the other one also. So you should be able to coherently access the memory. That is a key advantage of this. It will be, it can be used in hyperscale data center and HPC kind of a server going forward. Right? You would have seen this in multiple forums. This is how you can connect to OpenCAPI. If you have a CPU, you can connect your standardized memory with the OpenCAPI 3.1, right? It can be DDR4, DDR5, whatever it is. And then you will also have a OpenCAPI 3.0, which will be able to connect accelerator. For example, if you have an FPGA based accelerator, you should be able to connect. And then network card, advanced memory can be HBM or HMC, and then coherent storage controller also. So everything can be connected with one single interface. So that's a key advantage. So like I said, OpenCAPI specifications, you can get it from opencapi.org. You can register and download, right, if you want to develop. So this is how the future memory subsystem with the OpenCAPI will look like. The processor chip which will have data link layer, transaction layer. There are two layers, two different specifications available, and you can connect that with the SCM, storage class memory, and then you can also connect with the regular memory, DDR4 or DDR5, and you can cascade that and then try to connect to storage also. This is like, it will give you two tier memory, right? And then you can, this is a typical which we use in main memory bus, right? So you can try to connect this way also. So the advantage of this is, you can attach any kind of devices, any kind of compute devices. It will reduce the latency drastically because it operates at 25 Gbps. One link operates at 25 Gbps. And then agnostic interface, which will allow all the new memory technologies, which is like STM RAM, RERAM, or whatever it is. And this is a common physical interface which I told it can be used for multiple other purpose. So this is a typical OpenCAPI attached memory, 25 GB IO. You can connect STM RAM, MRAM, RERAM, PCM, 3D crosspoint, and then standardized memory directly with the DDR4 or DDR5, right? And I also wanted to say this, that there is a competitive other IO interfaces which are available in other companies who is trying to develop, like HPE or CCIX and Gen Z, right? Gen Z is predominantly used in storage side, which will go up to 300 gigabytes, right? But OpenCAPI is more focused for enterprise server, right? Okay, the final set of slides. Any questions so far? I've been keep talking.
So OpenCAPI, that is sort of being envisioned as a system concern of PCIe. So
Yeah, correct.
PCIe is also core into the process.
Correct. Yeah, similar to that. Okay. Yeah. I am not able to follow. Mm-hmm.
Say DDR4 to DDR5, what's the major contribution?
So DDR4 to DDR5, for example, if you the device density is 8 gigabit for now, DDR4. If you go to DDR5, it will go to 32 gigabit. So 9 DRAMs put together in DDR5 will give you about 32 gigabyte. Currently, what is available in 3D TSV is 128 gigabyte. It will go up to 4 times bigger than that, which means that 512 gigabyte you will get in one DIMM. So density is a bigger advantage, and the speed also. For example, DDR4 can go up to 3.2, DDR5 can go up to 6.4. And in order to handle that, you need to increase the IO capability, which is why we go from 12 gigabits, which we are currently using, to 25. Okay. Mm-hmm. Mm-hmm.
such amount of data, or will there be a point of serialization where, say, the capacity will change so that, like, to
Yeah, so
that amount of data to a memory controller, so, like, if the width is less, then it needs to serialize.
correct. So that's a good question. I wanted to say that, but then I forgot to tell this. In this case, if you see DDR4 and DDR5, we connect with the open cap itself, which means that we are not really going ahead with parallel bus. We will be converting that into a differential interface, which will have a buffer. So basically, open CAPI will go and interface with another chip, which will convert this parallel to serial and then send it to the processor. That is one way. The other way is the buffer can be sitting in the DIMM itself, where it will take differential inputs and then give it to the DRAMs. That's how it is taken care. Okay. So IBM Power Processor Roadmap from 2004, as you can see, Power 5. Right now we are in Power 9. We are currently working on Power 9 Plus and Power 10. Right. So this is extremely analytic, and this is used for all the artificial intelligence kind of a processor, applications. And it has got on-chip accelerator and very specific to big data analytics. I'm sure this processor will be able to leverage all the requirement from the new era. Like I said earlier, there is two way of connecting the processor. One is direct attached and the other one is buffered one. As you can see, you have about 24 core DDR. You have new CAPI, which is called open CAPI, and then CAPI and all other interfaces which will be attaching to the IO, right? So currently, I think last week we did announce this Power 9 system in Supercomputing Austin conference, best server for AI, right? As you can see, there is a motherboard, DIMMs, processor, GPUs, it's a full-blown view. This can be used for all the modern applications like analytics, HPC, and AI. It can be used for ML also, right? And as an university, I think you can participate in Open Power Foundation, becoming a member, right? You can contribute to develop some of the power-based ecosystem development, and you will be able to get all the server details and all other tools and documents which is required for you to develop the new technologies and work with the power ecosystem. So we range from chip all the way up to research, right? There are multiple universities already working with us, IIT Bombay, IISc, and other companies. Final slide, I would like to thank my mentor, who is an IBM fellow, Hilary Hunter, Gary, Adam, Anand, and my friend. And I also want to thank Kalyan for working with me on multiple other things, right? Some of the reference. Okay, I'm done. I'm on time.